Thank you very much. Muchas gracias. Good evening, and thank you for that welcome. And thank you for being here this evening. I hope you will be pleased to learn that you are made of star stuff, and I will show you how. But first, some student answers to questions. Is that correct? No. What is H2O? Sorry. I can't do it. Can't do it. H2O is what? Tell me. Water. CO2 is what? Tell me. Carbon dioxide. Yes. So that was a student's answer to a question. You do not need to know the question. Here is another student answer to a question. These are not British student answers. There is a website where the best student answers are copied. So, we're going to talk about what we are made of and how that stuff came to be in our bodies. So the first question is, what are we made of? And I'm just going to turn this screen around a bit because the other one is too big. So, in our bodies, there is a lot of water. What is water? Please tell me. H2O, yes. So, water is hydrogen and oxygen. A lot of our bodies are water, so there is a lot of hydrogen and oxygen. But we're not just water. There are other things as well. There is carbon in our tissues. There is calcium in our bones. There's iron that makes our blood red. And there are a number of other chemical elements that are important. Potassium, sodium, phosphorus, things like that. But I am going to focus on I am going to focus on these ones. Physicists take an overview like this. So tonight you will not have many details, just the big picture. Okay, so when we were born, we were much smaller. This sort of size. You are bigger now. your body has more atoms now. Where have those atoms come from? Please tell me. Food. And maybe, but yes. So we have taken on atoms through our food and our drink. So let's think about the food. We eat fruit, grains, vegetables. We eat animals. Well, animals eat grains and vegetables and things. So let's think about the fruit and the vegetables and the grains that we eat. So a grape starts very, very small and grows. It gets more atoms. Where does it get those atoms from? From the earth and the rain a bit, but yes. So when we eat food, we are eating earth or atoms from the earth. So to understand where our bodies have come from, we need to understand where the earth has come from. That one. Now, I think in the end it is going to be simpler if I go right back to the beginning of the universe, the start of the universe, and work forward to today. So we're going to take a very, very big step. Maybe? Yep. To talk about the origins of the universe, the beginning of the universe. And our understanding now is that the universe began, it had a beginning 13.7 billion years ago. That is how old the universe is. And it began with a very big explosion, which in English we call the Big Bang. All of the universe, all of space, all of matter, all of energy, everything, and time as well, started with the Big Bang. And maybe you are wondering, what was there before the Big Bang? Before does not make sense, because time started with the Big Bang. There is no before. Or put differently, that is a non-question, and I cannot answer a non-question. So the universe started very, very small and went bang and exploded and spread out. At the beginning, it was fire, energy, a big ball of fire and energy, but it gradually expanded and cooled, got a bit cooler. There is a lot of light, blinding light, you cannot see. And as it cools, expands and cools, some of that light energy turns into solid stuff, particles, because E equals mc squared. Einstein. E is energy, light, for example, and you can take energy and make matter. So although the early universe was full of light and energy, gradually some really solid stuff began to form because E equals mc squared. But it's still very hot. After a few minutes, the temperature is about 1 billion. 1 billion what? 1 billion centigrade? 1 billion Fahrenheit, she's British. 1 billion absolute? Yeah, well, it doesn't matter. Because it's 1 billion, it's big. So, very hot, but even so, the nuclei, the centers of some atoms begin to form. And the first one to form is the nucleus of hydrogen, and it remains the most common. It's a very simple nucleus, it is just one particle. But after a while, some of the particles join up, and we get helium, and we get deuterium or tritium, which are heavy hydrogen. So we've got a few chemical elements, but hydrogen, helium, and tritium will not make us. So no life at that stage, and it's too hot anyway. So using this kind of diagram that maybe you've seen hanging up in schools, in chemistry laboratories, I'm going to explain which elements we've got. This in English we call the periodic table. It lists all the chemical elements. It starts with the lightest. Here is the next lightest. Then you jump back to the next line, lithium, beryllium, boron, carbon, nitrogen, etc. And you jump back to the next line, and so on. And as we go through it like this, we're getting bigger and bigger nuclei, heavier and heavier nuclei, and ultimately heavier and heavier atoms. But to begin with, we've got hydrogen and a little bit of helium. That will not make us. So, no people. Saying it again, for the elements that we particularly need, we've got hydrogen, but none of the others. So there could not be life very early in the universe. I wonder if here you have a children's story about a little girl who is out in the forest, and she goes to a house. Yes, some people are nodding. The house is empty at that moment. There are 3 beds. There are 3 chairs. And the house belongs to the bears. Father bear, mother bear, baby bear. You have that story here? Good. So you know that Goldilocks finds Father Bear's chair too big and Mother Bear's chair too soft. But Baby Bear's chair is just right. Excellent. And she finds Father Bear's porridge too hot and Mother Bear's porridge too salty. But Baby Bear's porridge is just right. And Father Bear's bed is too big and Mother Bear's bed has some other problem, and Baby Bear's bed is just right. Professional scientists sometimes can behave like children. Where we have a situation which is just right for something to happen. We call it a Goldilocks effect. And there was a Goldilocks effect early in the universe. So here we have time. The Big Bang is back that way. Us and the future are way off there. And here we have 1 second after the Big Bang. Here we have 3 minutes. And between 1 second and 3 minutes after the Big Bang, conditions are just right for these hydrogen and helium nuclei to form, particularly the helium. After 3 minutes, everything has expanded so much that particles never get together. They stay separate, and they can't join up. Before 1 second, everything is very hot and very dense, and it's all rushing around like fury. And if something gets made, along comes zook, and they split up. So only between 1 second and 3 minutes can we make some bigger atoms, bigger nuclei of atoms. It's this one. Yeah. So early in the universe, before about 3 minutes, only hydrogen and helium get formed. There might be a little bit of lithium and beryllium, but they probably don't last. So this explosion and the expansion and the cooling means that the universe at its beginning did not create the elements that we have in our bodies. Those elements have come from later in the life of the universe. So where was that? So the other elements, we've got hydrogen and helium. We need the stars to make the other chemical elements. So this is part of the constellation of Orion. This is known as the horse's head. There's some nice pink, red gas here. In astronomy photographs, you often see pink or red. It's hydrogen. Those who have had a chance to study physics may have seen a hydrogen lamp in a dark room and looked at the spectrum. There's a very strong red line. Whenever you see an astronomical photograph with some red patches, you can say, ha, hydrogen. And you will be correct 99.99% of the time. So red patches, hydrogen. There's dark material here. Do you see there are many more stars up there than there are here? This dark material has cut out the light from the distant stars, and you only see a few stars that are this side of it. It's like a curtain. Whoops. No. Oh. All right, okay. We can recover. Okay. So the dark cloud is like a curtain drawn across the sky. You only see the things that are your side of the curtain. And in this case, it's just a few stars. But this dark cloud, this curtain, is very important for our story and for us. So there are some dark things in our background. In that dark cloud, there are particles of gas, maybe dust. They are milling around. By chance, maybe you get a little group, a little knot. This has some extra gravity and will pull in one or two more particles, which puts up the gravity, so it pulls in some more particles, which puts up the gravity, so pulls in some more particles. And the knot grows and grows and grows and grows. And as it grows, the temperature in the middle goes up and up and up. And ultimately, the temperature in the middle has got so high that nuclear reactions start. It becomes a nuclear reactor, doing fusion reactions for those who want all the details. So when the temperature in the middle reaches about 10 billion degrees Kelvin, nuclear reactions start. And in particular, hydrogen converts to helium, and then helium converts to carbon. And both of these give out energy, and there is a star that shines. We have created a star. So a young star will look like this. In the middle, there are nuclear reactions converting hydrogen to helium, and out here, there is hydrogen. But still a long way from making life. No carbon, no iron, no oxygen, yet. Then, the helium that we have made inside the star can start doing nuclear reactions. We get helium formed from 4 hydrogens, but if we take 3 heliums, we can make carbon. And that's one of the elements we need. So inside the young stars, there can be hydrogen converting to helium and helium converting to carbon. And the young star now looks like this: hydrogen on the outside, hydrogen converting to helium, helium converting to carbon. So of this list of elements we've now got hydrogen and we've got carbon, but still no oxygen, calcium, iron or potassium. So still no life, not yet. Our sun is a star that has been converting hydrogen to helium. It will not go any further. The sun will ultimately die, and we will die unless we have got lots of nuclear energy or something like that. And the universe still has only a few chemical elements, not the hundreds that we know of today. That one. Actually, I will go back a moment. Bigger stars than our sun can do more stages. So we look now to the bigger stars to see how we get more chemical elements. And for example, a group of stars like the Pleiades, the 7 sisters, are bigger stars, and they are making more chemical elements. So we will now talk about the bigger stars. Bigger stars like the Pleiades can take carbon and convert it to, where am I? This is a very big screen and I don't want to fall off the edge. Carbon, we will get neon next, and sodium, neon sodium and magnesium. And in making those chemical elements, the star gives out energy. So it will shine for a bit longer. one of these Pleiades stars, maybe for 600 years. Only 600 years. The star, if it's big, can also take, even bigger, can also take neon and convert it to oxygen. This is one of the things we need. That process will keep the star shining for about 1 year. So in 1 year, the star makes oxygen. This time scale is getting rather short. The oxygen can be converted to silicon and that keeps the star shining, but only for 6 months. The silicon can be converted to sulfur, and then to argon, and then to calcium. That keeps the star shining for 1 day. What's going to happen? And the process goes on till the star has created iron and nickel. Now, iron, no, it's not a good fuel. You cannot convert iron to anything and get energy out. If you try converting iron, you will absorb energy. You will not give it out. So the star has a problem. For the physicists in the audience, you cannot fission iron and get energy out. You cannot fuse iron and get energy out. Iron is the pits. Maybe useful in other ways, but as a nuclear fuel, it is a disaster. So the star has a disaster. By this stage, the star looks like an onion with lots of different chemical elements, starting at hydrogen and running through to iron. So of the elements we need for life, inside this big star, there's hydrogen, oxygen, carbon, calcium, iron, potassium, and those other things. But they're locked inside a star. And you're not going to make human beings inside a star. It's too hot. The star then explodes. It's a catastrophic explosion. Everything gets thrown out into space, or very, very nearly everything. And it ends the sequence I've been talking about. We had quite a recent example of a star exploding. This is a photograph of a small galaxy near our galaxy. It's a satellite of our galaxy, and it's called the Large Magellanic Cloud. It's in the southern hemisphere. It's named after Magellan, the explorer, but it becomes Magellanic, and it's hard to see Magellan in that. So the Large Magellanic Cloud has many, 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 many stars, and some hot gas which glows pink red, which means red gas is what? Hydrogen. So there's lots of hydrogen, and there's one star down here marked with an arrow. To be absolutely clear, the arrow is added after the photograph is taken. There are not arrows in the sky telling us which star to watch. But watch that star. It has exploded. It was one of these big stars with all these layers ending up with iron. And because iron is the pits, you cannot do anything with iron and get energy out, it explodes. And it has wrecked the star, except maybe for about, 5%, 10% of the star. And it's gone, basically. But sometimes with death comes life. I think I will skip that one for the moment. Oh, no, I can't skip that one. I have to go back. Okay. So that star has, in its process, produced a whole lot of chemical elements. And with the explosion, they are thrown out into space, distributed with energy. This photograph shows the remains of one of these exploding stars. For those who are interested in astronomy, it's the Crab Nebula. It was observed to explode in 1054 AD. The Chinese spotted it and recorded it, so we have a good record. And this is the debris from the explosion. And in about there is the remainder, the core of the star that exploded. And that is helping keep this debris shine through a rather more complicated process that I won't talk any more about. But that's perhaps the best known example of a star that exploded in living memory. And it doesn't happen very often. So we've been lucky to have one in our lifetime explode. Now, I have to go back again and say a bit more about this one. Sorry. In the center of this, I said there is the remainder of the star. It's what we now call a neutron star. And neutron stars have turned out to be quite important. But let me just pause and recap. We have had stars create the chemical elements, some of them at least up as far as iron in that table. And when the star explodes, all these chemical elements get distributed. And so that material spreads out. Some of it gets gathered into another star, a new young star. Some of it gets gathered into planets, like planet Earth. A lot of the material of planet Earth has come from exploding stars. We reckon from 3 different explosions. So if I try and mime this and drive the technicians crazy. Here is a dark cloud. There's a little chance alignment of particles. Extra gravity pulls in more. Gravity goes up, pulls in more. Gravity goes up, pulls in more. Gradually becomes quite a big mass of particles. Temperature in the middle goes up, and nuclear reactions start. Hydrogen converting to helium. Brrr, runs out of hydrogen. The helium converts to carbon. Brrr, doesn't last as long. The carbon converts to all these other chemical elements. Brrr, 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 and some of the material from this explosion trickles over here to another dark cloud. The material coming over includes some iron and some calcium and some carbon from that explosion. Here there's some particles of gas and dust joined by the carbon, the calcium, the iron. Little knot, gravity. Gravity gets a bigger knot, gets hot in the middle, starts shining. Brrr, till it runs out of hydrogen, starts burning helium. Brrr, till it runs out of helium, starts burning carbon. Brrr, 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 and material gets spread out through space. And some of it spreads over here, where there is a dark cloud with particles milling around. The particles here are the particles that were here in the beginning, plus some stuff from the first explosion, which has now got here, plus some stuff from the second explosion, which has now got here. So this material has some iron and some calcium and some phosphorus and some carbon and some oxygen. And this turns into a star that we call the sun. Our sun is a third generation star, and it's made up with material that was here, plus material from 2 previous explosions. So this gas and dust gathers, and the sun starts shining. There's some material left over, which becomes the planets. And that's how the sun and the planets came to be. And a vital part of this is the death, the explosive death of 2 previous generations of stars. So we are really dependent on the stars, exploding stars, the death of stars, to give us the chemicals that we need for life. If we haven't had in our history 2 exploding stars, typically on average, we would not be here, because there would not be the carbon, there would not be the oxygen, there would not be the iron. Now, for those of you who know your periodic table, I have only taken us as far as iron. What about the chemical elements heavier than iron? Interesting things like uranium, thorium, indeed quite a lot of elements. We're really only about halfway up the periodic table. What about all the other chemical elements heavier than iron? For a long time, we weren't very sure how this happened. There was one idea that's probably true, although it may no longer be the main source. Maybe in the star you can take the heaviest element you've got, maybe it's iron, and you can add particles to it. So iron is here in the table, you add a particle, make the next biggest. Add another particle or 2, make the next biggest. Add another particle or 2, make the next biggest. And that way make the chemical elements that we have here on Earth, which are heavier than iron. Except some of these chemical elements are radioactive. So if I land on a radioactive one, it goes and you're away back here. Okay, nature's very patient. Add a particle, make a bigger one. 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 Add. So, how do we make the really heavy elements? How did uranium come to be? Indeed, how did anything heavier than iron come to be? And we have, whilst what I've been demonstrating can be made to work, you add a particle, okay. You add a particle, okay. You add a particle, okay. You add, ooh! If I jump quickly, I'm okay. And you add a particle, and you add a particle, and you add a particle, and then you have another radioactive one. Woo! Add 2 particles quickly. That can happen, but we have recently found a better way of making the really heavy elements. And yes, when one of these stars explodes, the core is left behind. It's what's called a neutron star. There are a number of neutron stars around the place because over the ages there have been a number of explosions. If by chance you could make 2 neutron stars collide with each other, in that merger explosion event, you can easily make some of the very heavy elements. It's a doddle. But you have to make two neutron stars collide. And for a long time, this was a theory. Does it really happen? Don't know. What's the evidence? No. Zilch. And then, not very long ago, when there was a new kind of detector opening up a new spectrum, a gravitational wave detector, it detected a collision of two neutron stars. And if you can get two neutron stars to collide, you can make lots of heavy elements. You just order it, and it turns up. So we now believe that the very heaviest elements are made occasionally in these kinds of collisions. But that's getting very esoteric. We do not need those heavy elements. Up to about iron gets us going quite nicely. And we know how we make those. So I've done most of this miming. I have demonstrated that I am crazy. But let me just summarize again for you. In our bodies, there's hydrogen, oxygen, carbon, calcium, iron, and quite a few other chemical elements. Hydrogen was around from very soon after the creation of the universe, from very soon after the Big Bang. But all the other chemical elements I have listed have been created inside stars or in the explosions of stars or the mergers of stars. So virtually all the atoms in your body have come from stars. We are children of the stars. We are stars. Thank you.